Is it okay? I really don't know what about that's today. I found out like my last number, yeah. But it's fine, I'll just study at one. I'll wait for these. I can't know, okay, that's the truth. Okay, okay, one is for my other. And then one is for my other. She doesn't have a house that she can. She could taste it. My family. It's easier. The other two are for us.
Page 2.
I know one is the last page of the. I don't know. You can do copy. This one? Thank you.
Right, so I want to recap the steps that we went through with solving differential equations. We'll go through a couple more examples, and then today we're talking about solving or these word problems. Now, the word problems are not too difficult after we understand how to structure the information. It's all using the same equation, so it's not too bad. The more important thing is being able to know how to solve these differential equations. So if you go to page, we're gonna work through problems on page 2, but I just want to kind of run through the steps and also review the things that the problems that we did do on page 1. So the first thing we do is if we're solving differential equations, again, the purpose here is trying to get from the derivative level up to the function level. So differential equation again just means an equation that has derivatives in them, or a derivative equation. So the first thing we do is if we see y prime, we write it as dy over dx, or dy over dt, depending on what the independent variable is. Usually it's dx, or usually it's x, but it could also be t. And we always like to cross multiply. If we cross multiply, we can get our x's, we can get our dx and our dy in their right locations. And then once you cross multiply, we can divide if something is out of place. It's okay to have x's and y's in the denominator, but we definitely need dy's and dx's up in the numerator. And then we take the antiderivative of both sides. We treat both sides like a separate problem. And once we find the antiderivative, could be power rule, could be use substitution, whatever the process is, then we're done with the calculus, and then the algebra portion is just trying to solve for y, whatever it takes to get y by itself on the left side. And then along the way, you may also be asked to solve for c to convert your general solution to a specific solution. And then so that's the whole process, and we're just seeing the different variations of those types of problems. Okay. So on page 1, we did this problem right before the day before the quiz. The steps that we took, we separate the variables as well. We try to get a fraction equaling a fraction, so we can cross multiply. So I subtracted that 2x over to the left side, put a 1 in the denominator, cross multiplied. Now, some of the easier problems allows us to just get full separation just by cross multiplying, but the whole purpose is bring everything up to the numerator and get your dy dx in sets, and then decide if the x's and y's are still out of place. If they are, you can divide them on the other side. And then once we have those set, we take the antiderivative of both sides, identify the appropriate rules. In this case, they're both power rule. Plus c shows up on the right side. And then the rest is just algebraic steps, just trying to get y by itself. Here I multiply both sides by 2, I take the square root, and I solve for c. And then you're dealing with the square root, you're having to choose between your positive and negative square root. If you're choosing between positive and negative square root, look at the y value of your order pair. The y value order pair is going to match whatever solution you want. If it's a positive y value, you want a positive square root. If it's a negative y value, then you want a negative square root. And not every differential equation is going to come out to be a square root problem, but if it is, then just understand there's two solutions available, but you only have to choose one of them that is meeting where that point exists. All right, so we'll walk through the steps slowly for number 4 and number 4 and 5 here. And page 2. All right, so it says find a general solution to y prime equals 6 cosine of pi x. Then find the particular solution if the function passes through the order pair 1, 2. So we're going to ignore that second sentence for now. We're going to get to the general solution first before the order pair can apply to our steps. Okay, so first thing I like to do is just get that y prime to be more descriptive. I want to see the dy dx. Put a 1 beneath so I can get that fraction going. Cross multiply just to get the dy dx's in their proper places. So my first priority is just trying to get the dy dx's in their right places, okay? Both in the numerator, one's on the left, one's on the right. So that's what I'm trying to get to begin with. And now I'm going to take a step back and ask myself, okay, do I have full separation? Do any of the x's and y's have to be moved? Okay. So do we already have full separation? Yes. Okay, so in this case, we don't have to move anything else because the y is already with a dy, the cosine, the x is already with the with a dx. Okay. And we talked about how we want to keep the left side as minimal as possible. If there was any leftover coefficients here, I would go ahead and move it to the right side because the more minimal we can keep the left side, the easier the process will be when we're trying to solve for y. Okay. All right, so we've done everything that we can on the separation side of things. So now we can take our antiderivative. Left side, what rule can we apply? Power rule, right? So y becomes y squared over 2. Technically, there's a plus c, but we know we can just save that plus c for the right side since we're going to group all the plus c's together. Now, the right side is going to require what? Yeah, got to be a little bit of use substitution. Okay, use substitution. Now, I'm going to go through the full steps, but this is easy enough for you to potentially jump to the antiderivative. Do you know what's going to come out of this pi x? Pi, but we got to put it in the denominator. Okay, so with use substitution, it's kind of like chain rule, but it's going to be the derivative, but it's going to be flipped. Now, if you don't want to have to memorize that process, you're more than welcome to go through and show all the steps. Okay, I just want to give a shortcut to students who feel like they can make that jump, but if you want to see all the steps, I'll show all the steps here. Okay, so du dx equals what? Yeah, pi. What? Yeah, just pi, right? Sorry, my bad. Yeah, just pi. Dy dx, du over dx equals pi. The x goes away. Right? Cross multiply. Right, dx pi equals du. Solve for dx. So you see that pi x is going to produce pi, and that pi is going to end up in the denominator. Pull the 6 out in front. Pull the pi out in front. 6 over pi, integral the cosine of u. Cosine becomes what? Sine. And then replace the u back in terms of the pi x. So you're left with 6 over pi sine of pi x plus c. So the shortcut I was talking about is if you recognize that pi x will produce pi and that's going to end up in the denominator, you could potentially jump from this step to this step without having to go through all this. Right? But I don't want you to feel like you have to make this jump. If you always want to go through u substitution, you're more than welcome to, so you can get, whatever is going to allow it to be clear in your head. I want you to take those steps. But if you can make this jump, that's also an option for you. So we're done with the calculus, right? We taken care of the antiderivative. We have our quote unquote general solution, but we do want to do some cleanup here, and eventually we do want to solve for C. And we do want to update this from a general to a specific solution. I'm going to move over to this side here. All right, I do want to solve for C, but I just want to do a little bit more cleanup. I want to get this equation to look a little cleaner before I plug in my order pair. But really, you can find your C value at any moment in time. As soon as the C shows up, you can put it in and solve for C. You don't have to do it the way that I'm doing it. But to me, I just want to plug in my order pair at a point where I feel is the easiest equation to plug in. So I'm going to just get rid of that 2 here. And by get rid of, I just mean multiply everything through by 2 so I can maintain balance. So distribute 2 through, I get y squared is equal to, what does this term turn into? 12 over pi. Plus what? Good. 2c is still c, so I'm just going to let that 2 get moved into that c. Okay. Technically, we could do square roots. Eventually, I am going to do a square root, but I want to just solve for the c value at a point that that I feel is the easiest version to plug into. So I'm going to start updating my general to I'm going to start with for c and then eventually update my general to a specific. So 1 goes in for x, 2 goes in for y, and I'm just trying to solve for c. Pi times 1 is just pi. What's sine of pi? Yep, 0, right? So 12 over pi times 0 is just 0. That makes it easy. C is just equal to what? So I'm going to take that 4 and put it in where I started making my substitutions. Now I'm getting closer to, I have my specific solution. I just want to do a little bit more work to try to get that y perfectly by itself. Yeah. Right, because it says find a particular solution. So particular solution just means the solution with the c replaced. Right? A general solution is an equation that has a c in it. A specific or particular solution is an equation without the c in it. Well, I need to solve for c first. Right? Are you asking why not solve for c earlier? Okay, why not put it in this step?
Yeah.
Because I didn't plug in my order pair at this step. I plug in my order pair at this step. Because these are slightly different equations. I don't want to plug in an order pair and solve for C and put it into another equation because then the C is not quite matched up, right? So you can, I mean, if I solve for C at this point, then I would plug the 4 in here, or it's going to be a different C value, but I'll plug that C value here. But yeah, you want to plug it into the equation that you began your substitution in. All right, any other questions up to this point? All right, so we're almost there. We want to solve for y. So to solve for y, what's our last step? Square root, right? So take the square root, but what's going to show up in front of the square root? Plus or minus. So that means there's a decision that we have to make. Now, not every equation is going to end up being a square root where you got to make this decision, but in this case, we do have two solutions and we can't keep both of them. There's only one of them that's going to apply. How do we know which one to keep? Look at the y value. Okay. The y value of your original order pair, that's a positive, so therefore we're going to keep the positive. Yep, that's it. All right, number 5. Solve y prime equals x plus 1 times y. What's the first thing that we can do? Yeah, let's get that y prime to be what? dy over dx, yeah. Now again, do not lose the set of parentheses, okay? So whenever you see a set of parentheses in a differential equation, it's not there to hinder you, it's there to help you, okay? So you want to leave those parentheses because they're trying to help you separate the variables apart or make it easier for you to see the different parts of your equation, right? All right, so next step, go ahead and cross multiply. Okay. Cross multiplying doesn't guarantee separation of variables, but it will place your dy and dx's in their right places. All right. Any questions so far? Okay. Now look, your dy dx's are locked in. Those we're not going to move them anymore. Those are where they should be, up in the numerator, apart from each other. dy on the left, dx on the right. Now, do we have full separation though? All right. So what needs to be moved? The y. All right. So how do we move the y? Divide it. So if I divide something over, it's going to end up where? Denominator, right? And I think this is where I see some students struggle a little bit. I should did what I wanted you guys not to do. We divide that y over to the left side. But I do think that some students feel that this doesn't quite look right, so they end up pushing that y to the numerator, make it y dy, and that's not the same thing. All right, so if something is meant to be in the denominator, go ahead and leave it in the denominator. We have a rule to handle this, but just make sure that algebraically, wherever y and x's land, that's where they need to be. Okay. All right, so I'm going to rewrite this left side here and maybe put it in a form that feels more recognizable. If I push that dy out in front, I can make it 1 over y dy. I can drop the parentheses on the right side now that the nothing is impacting it. But hopefully we can see the distinctive rules that need to be applied on both sides. The left side we can handle using what? This is 1 over u du, right? Which is natural log. So I don't have to go through u substitutions. It's just one variable here. I can just keep everything in terms of y. And then here, both these terms are, I can apply what? Power rule. Yep, x becomes x squared over 2 plus x plus c. Okay. Now, up to this point, you've earned the majority of the points because you've separated the variables, you've taken the antiderivative. Now, the last thing is just to solve for y. Okay. So I'm just doing whatever I can to try to get y by itself. Y is stuck inside that natural log, so I'm going to involve exponential function e, because I know e and natural log have a way of undoing or canceling each other out. E and natural log cancels out. It's important to note that everything that you see on the right side has been moved up to the exponent level. Okay. Now I want to do something special with that c here. Okay. So this is what I'm going to do. I'm going to keep the x squared over 2 plus c together. Sorry, plus x together. But I'm going to separate that c away from the rest of this expression. So I'm not going to put a plus now. I'm going to put a times e to the c. Again, I'm using this property here that says if I have a to the m plus n, I can separate them into a to the m times a to the n. So if I want to bring a plus sign down to the base level, it's going to turn to multiplication. Right? But I could have separated these two, but I know these are all part of the variable expression, so I'm going to leave this together. I'm just going to separate that constant away from it. All right. So now what can I do with that e to the c? It becomes just a c, but now it turns to a multiplication problem. So I'm going to leave that, turn into a c, and I'm going to push it out in front. All right, final thing is I want to undo the absolute value. So I'm going to drop the absolute value, but I got to balance it with a plus or minus. But now what can I do with that plus or minus? I can just, yeah, it can just go away because of the c. The c will take in the plus and the minus value. Plus x, I keep writing plus c, it's plus x. Okay, you don't have to do all this step here, but I just want to show you that the absolute value does get taken care of. We do have a balancing act on the right side. So this is your general equation. Okay. They don't give us enough information for us to update to a specific, but this is all they're asking for here. Okay. Any questions? Yeah. Yeah.
So why do you have to plug it in at that? Why can't you plug it in sooner?
Good. You could. You could plug it in sooner. You can plug it in at any. You can even wait till the square root comes up to solve for c, which means that your c value may be different along the way, but once you clean everything up, we should end up with the same equation. But the reason that I don't plug in the c, I don't plug in the order pair earlier, is because I'm trying to find an easier equation for me to plug in my order pair. To me, this is an easier equation to plug in my order pair 1, 2 than the previous one with the denominator. Sorry.
Oh.
Yeah.
Okay, so you see how you have y squared equals 12? Or you put the plus 4, right?
Yeah, right there.
Okay, so why couldn't you put that y squared over 3 equals 16? No, I'm not saying not plugging this order pair, I'm saying why couldn't you just put the, like, once you figured out what C was, why couldn't you put it in an equation you have? But never mind.
Yeah, let me talk to you afterwards, guys. I think there's, because you're asking good.
Or returning to an 8, and then it wouldn't be the same C value. Like it would be a different, well, it depends.
Which is fine, because it would eventually work itself out at the end.
That was my question.
Okay.
It should just work out anyway.
Yeah, because the C value, as a, you know, all these different C values, they're all part of the same equation, but they're just different forms, right?
You plugged 1 and 2 in at the first equation, then you could put the plus, you could put those 4 there, but because we finished, because we started the substitution at the second equation, let's put the plus 4 into that one. You can't go back into the first equation after you find the C.
Yeah, and that's what I was trying to ask, but I was just trying to ask why.
Oh, okay. I can, yeah, so afterwards, I can always go through a different variation. We can do what you said and you can test it out. Okay, okay. All right. No, but I'm glad you're asking those questions, though. I don't want to ignore them. Number 5, I do want to point out, the biggest trouble that students have is this step, okay? Seeing that variable in the denominator gives a lot of students anxiety. They feel like they're doing something wrong, okay? So, and they end up making a mistake by bringing that to the top. So just be careful about that. I mean, sometimes it could end up in the numerator, but you got to convince yourself that algebraically that you do it, right? Don't just move it to the top because it feels more comfortable, right? Because we do have a rule that can handle this, okay? We just don't want our dy dx in the denominator. That's what we don't want, okay? But once you get that set, then you can decide, okay, whatever needs to be moved, I can move them appropriately. Okay. We'll do a lot more of this, but I do want to talk a little bit about today's notes. So page 5. Okay, so we have something called direct proportion equation. That means the two variables, x and y, are directly proportional to each other. So it comes in the form of y equals kx. Indirect proportion is where y and x are inversely related. So the x is in the denominator, but then the rate that they are related is given by that k. So that k is called the constant of proportionality. And so we're just basically trying to get these equations, these sentences into one of these forms and put them where they're supposed to be, either in this relationship or in this relationship. And then we're going to do the calculus to solve this differential equation. So number 1, it says if the rate of change of y. So anytime I see a rate of change, I'm thinking derivative. So this is going to represent y prime. Rate of change of y. Varies directly. So varies directly, that tells us it's going to take on this form. So we already have the left side. That left side is in this case is y prime, varies directly. So we know the k is going to be in the numerator as well as whatever it's talking about, varies directly with the value of y. So that means k times y. Okay. So the rate of change of y varies directly with the value of y. All right. Any questions so far? All right, so now that we've created the equation, we're just going to solve this equation. Okay. So let's go back to what we did on the previous page, right? Anytime I see a differential equation, I want to solve it. What do I do with that y prime? Rewrite it as a dy over dx. Okay. Now, something else I want to talk about here is that with word problems, instead of x being the independent variable, now we're going to switch over to t being the independent. Okay. So so in this case, we're going to let t replace x, but it's going to act the same way, okay, as x. Okay, we just have to, with these word problems, t will take the place of x. Okay. So I'll say dy over dt is equal to ky. So just have to adjust and say, okay, I'm going to treat t like I would x. Right? Cross multiply. One dy equals ky dt. So we have our dy and dt locked in. Those are the first important thing that we have to make sure are in place, and they are. Now, separation of variables. Do we have full separation? Okay. What's out of place? The y. So what do? Divide it. So it's going to end up in the denominator, right? Denominator on the left side. Remember, k is just a constant. So treat k like you would a 3 or 5 or 7. Okay. The variable in play is time, dt. Okay. So we left the left side as bare as possible. Only the essentials that need to be on the left side is on the left side. All right, so left side, 1 over y dy becomes natural log absolute value of y. Now, k is not the variable. We can't say k squared over 2, right? So k is just going to hang out in front. The variable is time. So imagine that there is 1 dt in front. So what's the integral of 1? T, yeah. So this becomes what? kt plus c. Does that make sense? Or if you want to think of it this way, you can push the k out in front and say it's 1 dt. The k stays, the 1 turns into a t, so then we merge it together, making kt plus c. All right, so let me rewrite what I have so far. All right, I want to solve for y, so what can I do? Raise both sides, base e. I know e and natural log are going to work itself out. E to the kt plus c are sitting up in the exponent spot. I know I want to separate them so that I can deal a little better with that c, but make sure that any plus sign in the exponent is not going to become a plus sign at the base level. You got to change it to a multiplication. Okay. And now e to the c is same thing as just c. So I can push that down in front. I can drop the absolute value because the c will absorb it. So now, from now on, if you ever see this relationship, ky equals K prime equals Ky, we can jump directly to this equation. Okay. So if we start with this, we can go directly to here, and that we're going to be able to skip the calculus step because we know that this is always going to end up with this. So number two, we're going to see this relationship. We're going to jump directly to our equation, and then our work is really just trying to solve this equation. So for these problems, we're going to skip the calculus step because it's all going to end up getting us to the same equation. Now, the algebra portion is just trying to solve for C, solve for K, and eventually do the prediction that they're asking us to predict. Okay, so it says the rate of population, the rate of increase of the population. So I'll let P represent population, rate of increase. So I know that's going to be a what? Rate of increase means, or a rate means P prime. Good, P prime. So I just want us to be able to write that down. P prime is proportional. So we know it's going to be in this form of y equals kx, proportional to the population itself. So P prime equals K P. Right? Same relationship as y prime equals ky, right? So we can do separation of variables if we want, but we know this is going to eventually turn out to be the same as this. Does everybody see that? It's the same thing here. Y prime equals ky, P prime equals kp. So I can say y is equal to oh, sorry, not y. This is now my variable is now p. So p is equal to ce to the kt. Right. So I'm just skipping all the calculus steps because I know where it's headed. It's the same problem, just different variable. Now, the two order pairs, the order pairs I'm going to be working with is time is an independent variable because we treat time the same way that we would x. In this case, the y is now the p. So my order pair is going to take on time followed by population. So instead of x and y, I'm going to say time and population. All right, so the rate of increase of a certain city is proportional to population. If the population in 1930 was 50,000, in 1960 was 75,000, what's the expected population in 1990? So with all these numbers, I like to organize them as order pairs it just feels more structured that way. And anytime I can take advantage of 0, I'm going to take advantage of it. So what's the earliest year that I see? 1930. So I'm going to let 1930 be t equals 0. That's my starting time, right? So I'm going to say at year 0, the population was 50,000. Right? 1960, how many years after year 0 is that? Or sorry, 30 years after my starting. So 30, comma 75,000. And then it says, what's the expected population in 1990? So how many years after the beginning? 60. So 60 years later, what's the expected population? So we're going to use this equation to help us make that prediction. But the reason why all these order pairs are provided for us is because this will help us fill in these gaps that we need. We need the C resolved, we need the K resolved. And then once we have everything filled out, we can make our prediction using the previous data. Okay, so anytime I see 0, I'm going to plug this in first. Okay. Anything with 0 will help us get down to a variable, solve for a variable the easiest. So 0, I can plug in for what? T, and 50,000 I can plug in for T. Okay. Right. K times 0 is 0. E to the 0 power is 1, right? Anything to the 0 power is 1. So C times 1 equals 50,000. Okay, so I know what the C value is, right? So now I'm going to take my general equation, I'm going to update it so that I can make progress along the way. So now I'm going to use my second order pair. Continue that process, and the hope is that this will solve my other missing information, which is the K. Right, so 30 plugs in for T, 75,000 plugs in for T. Yeah, okay. All right, this feels a little messier, but we're going to do things one at a time here. I think the easiest thing to combine together, we want to solve for K. So little by little, I want to strip things away to the other side. So I'm going to move that 50,000 over. So 75,000 divided by 50,000, I can use my calculator. It's going to reduce down to 1.5. All right, I want to solve for K, but K is sitting up in the exponent. Is there something that's available for me to allow me to get that K down? What can I introduce into the equation? Natural log, right? So natural log allows exponents to be more easily moved. Right, the 30K can drop down. What do you know about natural log of E? Just equal to 1, so I can just make it go away. So I'm just down to 30K equals natural log 1.5, divide both sides by 30. So my K is equal to natural log of 1.5 over 30. I don't want to do the decimal value just yet because I want to hold on to my exact value until the very end. So I'm going to hold on to that K value a little longer. If I get a decimal value, I'm losing my accuracy a bit earlier than I would like. So I'm going to update my equation now. This is my equation halfway updated, but now I can do the full update. I replace the C with 50,000. I replace the K with natural log 1.5 over 30. And now I can use this to make any predictions I want. So now I want to find out what is the population 60 years after we began in 1930. So I can plug 60 into the what? Into T, and then all of this can go in the calculator. That will give me a decimal, and now I can make my prediction for my population in year 60 or 1990. Okay, so now I can give my approximation, right? But if I give my a decimal value a little too soon, then it decreases my accuracy. So I know I'm still getting an approximation, but at least I can hold on to my exact value a little longer to improve my accuracy. Okay, so all that in the calculator will give us around 112,500. Yeah, there's a slightly different variation that I want to show you, but I'll show that to you on Monday. Just want to give you an update here. So Monday, I will check both your 6.3 and your 6.2 homework. I will send out a reminder on Sunday. Monday, we'll finish up some of the problems I want to do. And then another topic is slow fields. Okay, so we'll do that, but then we'll spend a good chunk of time just getting some additional practice with solving differential equations. We can get more comfortable. And then, but no assessments next week. And then after we come back from break, we'll have a review day before break, review day after break, and then test Thursday after break. Okay, all right, you come get your phones. Yeah.
I need to.
Yeah.